Welcome to our deep dive into the fascinating world of alternating current.
Oh, yeah, it's a good one.
If you've ever wondered about the electricity that powers our homes and so much more,
Hmm.
you're in the right place. You've brought some physics textbook excerpts,
Yes.
and together we're going to unravel the mysteries of AC,
Yeah.
from its basic principles to its role in everything from household appliances to metal detectors.
Yeah, it's really remarkable how much we rely on AC without even thinking about it.
Absolutely.
It's truly the backbone of our modern electrical grid.
So to start us off,
Yeah.
can you give us a quick refresher on what makes AC different from direct current?
Sure.
I know they both involve the flow of electrons,
Yes.
but something about the electrons doing the electric slide instead of marching in a straight line.
That's a fun way to put it. You're right.
Yeah.
Both AC and DC involve the movement of electrons.
Uh-huh.
But in AC, the electrons constantly reverse direction,
Okay.
oscillating back and forth at a specific frequency. Think of it like a pendulum swinging back and forth.
Okay, so the electrons are doing a bit of a dance,
Yeah.
but they're still moving energy around, right?
That's right.
Why is this back and forth motion so important?
Well, what's fascinating here is that this alternating motion
Uh-huh.
is what allows us to use transformers
Okay.
to easily change the voltage of AC.
Got it.
This is crucial for efficient power transmission over long distances.
Transformers.
Yeah.
Those mysterious metal boxes we see on power lines?
Mm-hmm.
They're like the electrical gearboxes of the grid, aren't they?
That's a good analogy.
But why can't we just use high voltage for everything? Why do we
You-
even need to step it down?
That's a great question. High voltage is excellent for long-distance transmission because it reduces power loss.
Okay.
But for safety and compatibility with our appliances,
Right.
we need much lower voltages in our homes and businesses.
So transformers help us strike a balance between efficient transmission and safe usage. That makes sense. Now, let's dive into your textbook excerpts.
Okay.
The first concept we encounter is how AC voltage behaves when applied to a resistor.
Right. When an AC voltage is applied to a resistor, the resulting current also alternates and has the same frequency as the voltage.
Okay.
They rise and fall together in sync.
So the voltage and current are doing a perfectly synchronized waltz across the circuit.
I like that analogy.
But how do we measure AC voltage and current if they're constantly changing?
Mm.
It's not like we can just grab a ruler and measure the height of the wave, right?
Yeah, that's where the clever concept of RMS values comes in.
Okay.
RMS stands for root mean square, and it gives us a way to represent the effective value of an AC quantity. It's like asking what DC voltage would produce the same amount of heat in a resistor.
I see. So instead of trying to chase the constantly changing peaks and valleys,
Yeah.
we use this RMS value as a sort of steady representative.
Right.
The textbook mentions our standard 220V household supply is actually an RMS value.
Right.
What's the actual peak voltage then?
It's surprisingly higher. The peak voltage of a 220V AC supply is actually around 311 volts.
Really?
Yeah.
That's why touching the live wire is so dangerous.
Exactly.
You're not just dealing with 220 volts, you're potentially getting hit with over 300.
Exactly.
Wow, that's a point. I'll definitely keep in mind next time I'm tempted to poke around in a wall socket.
Good idea.
Now, the textbook introduces something called phasers.
Mm-hmm.
These sound more like weapons from a sci-fi movie than tools for understanding circuits.
They might sound intimidating, but phasers are actually very useful visual aids.
Okay.
Imagine them as rotating arrows like the hands on a clock.
Got it.
The length of the arrow represents the amplitude of the AC voltage or current,
Uh-huh.
and the speed of rotation represents the frequency.
So instead of getting lost in complex equations,
Yeah.
we can use these spinning arrows to see how the voltage and current relate to each other.
Exactly.
That's pretty clever.
It is. Phasers help us visualize the phase relationship, which is crucial for understanding how different components behave in AC circuits.
Right.
Speaking of components, let's move on to inductors.
Okay, inductors.
Yeah.
Those are coils of wire, right?
Yeah.
Like tiny electromagnets.
Yeah.
What happens when we introduce AC voltage to them?
What's interesting about inductors is that they resist changes in current.
Mm.
When the AC voltage pushes electrons through the coil, it creates a magnetic field,
Right.
but the inductor fights back,
Oh.
trying to keep the current flowing at a steady rate.
So it's like the inductor is the stubborn one in the relationship.
Exactly.
Resisting any sudden moves the voltage tries to make.
You got it.
And the textbook mentions inductive reactance,
Yeah.
denoted by XL,
Mm-hmm.
as a way to measure this stubbornness of the inductor.
Yes. Inductive reactance is like a resistance specific to AC circuits.
Okay.
It depends on both the frequency of the AC supply and the inductance of the coil itself.
Got it. So the faster the AC voltage changes direction,
Yes.
the more the inductor digs in its heels and resists.
Exactly.
Fascinating. Now let's explore another key player in AC circuits, the capacitor.
Capacitors are like tiny reservoirs of electrical charge.
Okay.
They consist of two conductive plates separated by an insulator.
Uh-huh.
When AC voltage is applied, they store charge and release it in a way that actually leads the voltage.
Wait, so now the current is ahead of the voltage.
Yeah.
Did they switch roles in this electrical dance?
You got it. The capacitor, unlike the inductor, loves changes in voltage.
Okay.
As the voltage rises, the capacitor eagerly stores charge.
Got it.
Then as the voltage falls, the capacitor releases its stored charge, causing the current to surge ahead.
So in a way, the capacitor anticipates the voltage's moves,
Right.
making the current lead the dance.
Yes.
And we have another resistance term here, capacitive reactance, or XC.
Exactly. Capacitive reactance is similar to inductive reactance,
Okay.
but with a key difference. It decreases as the frequency of the AC supply increases.
So the faster the AC voltage changes direction,
Yeah,
the less the capacitor resists.
you got it.
It's like the capacitor thrives on high energy music.
A good way to think about it.
Now, what happens if we combine all these components, resistors, inductors, and capacitors, in a series circuit?
That's when things get really interesting.
Okay.
We create what's called an LCR series circuit.
Okay.
And to understand how current flows in this complex dance floor, we need to introduce the concept of impedance.
Okay. Impedance sounds important. Is it like the combined resistance of all these components working together?
You're on the right track. Impedance,
Yeah.
denoted by Z,
Uh-huh.
represents the total opposition to current flow in an AC circuit.
Got it.
It takes into account the resistance of the resistor,
Right.
the inductor reactance of the inductor,
Uh-huh.
and the capacitive reactance of the capacitor,
Yeah.
all working in concert.
So it's not just a simple sum, but rather a complex interplay of these different resistances, influenced by the frequency of the AC source.
Right.
I'm starting to see how the frequency of the music really dictates the flow on this electrical dance floor.
Precisely. And this interplay leads to some fascinating phenomena in AC circuits, one of which is called resonance.
Okay.
It's like finding the sweet spot where the circuit vibrates most efficiently
Yeah.
with the rhythm of the AC source.
Resonance, that sounds familiar. Is that how we tune a radio to pick up a specific station? Like
Yeah.
finding the right frequency for the circuit to sing along with?
You hit the nail on the head. Resonance in an LCR circuit occurs when the inductive reactance, XL, and capacitive reactance, XC, cancel each other out.
Okay.
At this magical frequency, the impedance of the circuit is minimized,
Uh-huh.
allowing the maximum current to flow for a given voltage.
So by adjusting the capacitor,
Yeah.
we can tune the circuit to resonate with a specific radio frequency and pick up that station's signal.
Exactly.
It's amazing how such a seemingly abstract concept like resonance has such a practical application.
It is, and this is just one example of the many wonders of alternating current.
I'm already hooked. We've covered a lot of ground in this first part of our deep dive.
Oh, yeah.
From the basic difference between AC and DC to the intricate dance of voltage, current, and reactance.
Yeah.
It's been an eye-opening journey so far.
Indeed. And we have plenty more to explore,
Okay.
including the crucial role of transformers, the concept of power factor,
Right.
and even how metal detectors utilize these AC principles to uncover hidden treasures.
Can't wait to delve deeper. Stay tuned for part 2 of our AC adventure,
Okay.
where we'll continue to unravel the mysteries of this electrifying force that powers our world.
It's going to be good.
I'm excited.
Me too. Welcome back to our deep dive into the world of alternating current.
I'm ready for more.
It's amazing how these fundamental concepts we've been discussing translate into such diverse and practical applications.
I know, right? We've already seen how AC principles enable us to tune a radio using resonance. What other examples come to mind where these concepts are put to work in the real world?
Well, let's talk about those big industrial motors you find in factories.
Okay.
Many of them are inductive loads, which means they cause the current to lag behind the voltage.
So it's like these motors are throwing off the rhythm of the electrical dance floor, making the system less efficient.
Precisely. This lag between the voltage and current is measured by something called the power factor,
Okay.
which tells us how effectively the circuit is using power.
Right.
A low power factor means we're drawing more current than we need,
Mm-hmm.
leading to wasted energy and higher costs.
That sounds like a problem. What can be done to improve the power factor and get those motors dancing in sync with the voltage?
This is where capacitors come to the rescue.
Okay.
By installing banks of capacitors in parallel with those inductive loads, we can counteract the lagging current.
Okay.
Remember how capacitors make the current lead the voltage?
Ah, so it's like bringing in a professional dance instructor to get everyone back in step. Yeah.
Exactly.
The capacitors compensate for the lagging current caused by the inductors, improving the power factor and making the system more efficient.
That's right. This is a common technique used in industrial settings to reduce energy waste and optimize power usage.
Got that.
Speaking of optimization, let's shift gears for a moment and talk about the safety aspects of AC.
Okay.
We briefly touched on those high peak voltages earlier.
Yeah.
What other safety considerations should we be aware of when dealing with AC?
Well, the textbook emphasizes that understanding the difference between RMS values and peak values is crucial for safety.
Right.
It's easy to forget that the actual voltage swings much higher than that average RMS value we use for calculations.
Oh, got it. It's like designing a roller coaster.
Uh-huh.
You have to make sure the structure can handle the highest G-forces,
Okay.
not just the average speed.
Right.
Similarly, when choosing insulation materials and safety devices for AC circuits, we need to factor in those peak voltages
Right.
to ensure they can withstand the most extreme swings in the electrical flow.
So it's not enough to just look at the average. We need to be prepared for those thrilling peaks in the electrical ride.
Exactly.
Now, what about grounding? I know that's a big part of electrical safety. How does grounding help protect us from those rogue electrons?
Grounding is essential because it provides a safe path for stray currents to flow to the earth.
Okay.
If a fault occurs in a device, instead of that current flowing through you and giving you a nasty shock,
Right.
it takes the express route to the ground through the grounding wire.
It's like having an emergency exit for any electrons that might get lost or go rogue.
That's a great way to put it.
Ah.
Now, let's circle back to the concept of impedance.
Okay.
We talked about how it combines resistance, inductive reactance, and capacitive reactance. But how does impedance actually influence the flow of current in an AC circuit?
Well, the textbook compares impedance to resistance in a DC circuit.
Right.
Just like a higher resistance restricts the flow of current in a DC circuit, higher impedance puts the brakes on current flow in an AC circuit.
Yes, but there's a key difference.
Okay.
While resistance is a fixed value, impedance varies with the frequency of the AC supply.
Got it.
This is because both inductive reactance and capacitive reactance change with frequency.
So it's like the AC circuit's resistance is constantly shifting depending on the tempo of the electrical music.
Precisely.
That makes it much more dynamic than a simple DC circuit, doesn't it?
Absolutely. And this frequency dependence of impedance leads to all sorts of fascinating behaviors, like resonance, which we discussed earlier.
Right.
Remember how we can tune a radio by adjusting the capacitance to match the desired frequency?
Right. We're essentially tweaking the impedance of the circuit to resonate with the specific frequency of the radio station we want to hear.
Exactly.
I'm starting to appreciate how all these concepts interweave with the frequency of the AC source acting like a conductor, orchestrating the complex dance of voltage, current, and impedance.
Precisely. Now, shifting gears again, let's revisit those transformers. You've probably seen them perched on power lines, humming away.
Yeah.
Can you recall the difference between step-up and step-down transformers?
Sure. Step-up transformers have more turns in their secondary coil than their primary coil, which allows them to boost the voltage.
Right.
Step-down transformers do the opposite. They have fewer turns in the secondary coil, so they reduce the voltage.
Excellent. And remember, it's all about the ratio of turns between the two coils. This ratio determines whether the voltage is amplified or reduced.
The textbook highlighted how essential transformers are to our electrical grid.
Yeah.
By stepping up the voltage for transmission, we reduce power loss over long distances.
Right.
Then, step-down transformers safely bring the voltage back down to usable levels for our homes and businesses.
Exactly.
It's a brilliant system.
It is. Transformers are truly the unsung heroes of our modern electrical infrastructure.
And I've covered a lot of practical applications, but let's take a moment to appreciate the historical journey that led to AC becoming the dominant form of electricity.
Okay.
Why do you think AC ultimately won out over DC?
That's a good one.
Well, the textbook mentioned a bit of a war of currents in the early days of electricity.
Right.
Thomas Edison was a big proponent of DC, While others like George Westinghouse and Nikola Tesla championed AC,
Yeah.
I'm guessing AC's versatility and its ability to be efficiently transmitted over long distances played a big role in its victory.
You're absolutely right.
Yeah.
With DC, the voltage drop over long distances was a major hurdle.
Right.
AC's ability to be easily stepped up and down in voltage, thanks to those ingenious transformers, made it the clear winner for large-scale power distribution.
It's fascinating how these historical decisions about which technology to adopt shape the entire electrical infrastructure we rely on today.
I know it is.
I'm starting to realize that AC is more than just a type of electricity. It's a powerful force that we can manipulate and harness to achieve incredible things.
Well said. And there's one more intriguing concept I'd like to introduce before we wrap up part 2.
Okay.
The textbook mentions something called wattless current in relation to purely inductive or capacitive circuits. You ever heard of that?
Wattless current. That sounds a bit like a paradox.
Yeah.
How can current flow without actually doing any work or consuming power?
It's a bit counterintuitive, I know.
Right.
Wattless current occurs when the current and voltage are completely out of sync,
Okay.
90 degrees out of phase, as we see in purely inductive or capacitive circuits. The current is still flowing back and forth, but it's not transferring any net power.
So it's like running on a treadmill. You're putting in effort, but you're not actually going anywhere.
That's a perfect analogy.
Yeah.
While wattless current doesn't directly contribute to power consumption,
Right.
it can still put a strain on the electrical system.
Okay.
Engineers need to consider it when designing and managing electrical systems to ensure everything runs smoothly and efficiently.
Wow, there's so much more to AC than meets the eye.
I know, right?
We've covered so much ground already, from the fundamental concepts to the historical context, and even the safety considerations.
It's been a lot of fun.
I'm ready to dive into the final part of our AC adventure.
Thanks.
I'm ready. In part 3, we'll wrap up our exploration by examining a few more intriguing aspects of this electrifying force that shapes our world.
Okay, great.
Stay tuned.
Welcome back to the final part of our deep dive into the world of alternating current.
I'm ready.
It's amazing how these fundamental concepts weave together to create such a powerful and versatile form of energy.
It is truly remarkable. From powering our homes to enabling wireless communication, AC is the invisible force that shapes so much of our modern world.
We've already covered so much ground.
We have.
But there's one more question that's been swirling in my mind.
Okay.
We've talked about how transformers can step up or down voltage, but what happens to the power during these transformations? Does it magically increase or decrease?
It feels like we're getting something for nothing.
That's a great question, and it highlights a fundamental principle of physics. Energy conservation. Transformers don't create or destroy energy. They simply change the relationship between voltage and current.
So it's like those physics demonstrations with the rolling balls.
Yeah.
One ball rolls down a ramp and sends another ball flying upward on a different ramp. The energy is transferred, not created out of thin air.
Exactly. In a step-up transformer, the voltage increases, but the current decreases proportionally.
Okay.
Conversely, in a step-down transformer, the voltage decreases, but the current increases.
So it's a balancing act.
That's right.
The textbook mentions that this principle is crucial for efficient power transmission.
It is.
By stepping up the voltage for long-distance transmission, we reduce the current, which minimizes power losses due to resistance in the wires. It seems counterintuitive that increasing the voltage actually leads to less energy loss.
It does seem counterintuitive at first, but it's a brilliant strategy to make the most of our electrical energy.
Right.
Of course, real-world transformers aren't perfectly efficient.
Right?
They experience some energy losses due to factors like flux leakage and resistance in the windings.
Right. There's always some energy lost along the way. But engineers are constantly working to improve transformer designs and minimize those losses.
That's right.
It's a good reminder that even in the world of electricity, there's no such thing as a free lunch.
Absolutely. Every energy transformation comes with some inherent costs.
Right.
But the beauty of AC is that it allows us to manipulate these transformations in ways that maximize efficiency and minimize waste.
As we wrap up our AC deep dive,
Yeah.
I'm struck by how seamlessly these concepts connect. From the fundamental principles of voltage, current, and resistance to the practical applications in transformers, motors, and even metal detectors.
It's a lot of stuff.
It's like a beautifully choreographed dance of electrical energy.
It's a testament to the elegance and power of physics.
Yeah.
These principles govern the behavior of electricity, shaping the technologies that power our modern world.
The key takeaway for me is that AC is more than just a type of electricity. It's a dynamic force that we can manipulate and harness to achieve incredible things,
Yes.
from illuminating our homes to enabling wireless communication. AC is the invisible hand that shapes our technological landscape.
Well said. And I hope this deep dive has left you with a newfound appreciation for the wonders of alternating current
I definitely do.
and a thirst to explore even more of the scientific marvels that surround us.
Absolutely. It's been an electrifying journey, and I'm grateful for your insights and expertise.
Oh, it's been fun.
To our listeners, thank you for joining us on this deep dive into the world of AC.
Yes, thank you.
We hope you found it enlightening and engaging.
We did our best.
Until next time, keep those circuits buzzing with curiosity.